It's recording. Just a second, it's taking a while to. So this is any body, okay? And this is a line segment in the body whose length is ds. Okay. Now, this body is subjected to some deformation, and when this body is deformed, something changes in this line. Maybe it has some rotation. Its new length is ds bar. Now, the accurate definition of strain is okay. If you simplify this,
Dr. Nick, where did you get this formula?
this is not a formula. This is the definition of strain. This is
Okay, yes. Then changing length, divided by original length.
there are so many types of strains, but really you have to take continuum mechanics level. You can know all of them. But this is the fundamental definition. To explain, if you simplify this, ds bar plus ds by 2, approximately this is 2ds, right? For small deformation, right? Right?
Yes.
When the deformation is small, ds bar and ds are not that different. So this is approximately 2ds. Now, if you cancel these two, this becomes our common change in length by original length. But this one is the more accurate definition, okay?
Yeah.
Okay, so now what is In quantum mechanics, the fundamental definition is one of the fundamental gradients that we deal with is this is defined as F. Okay. Or in Einstein notation, so whenever we say bar, it is deformed configuration. Without bar is undeformed configuration. Okay. This is F, right? So when you have dx bar, it can be written as F dx. Okay. Now, what is the length ds square? This is equal to dx1 square plus x2 square, right?
Yes.
So this is nothing but right?
Yes.
Okay, so dx bar is this. From the definition of deformation gradient, the vector dx bar, that means this ds is the length of the vector, that is dx bar plus dy bar dz bar. Generally, we don't write like that. We write as dx1 bar. Sorry. Okay. We write as dx2 bar j. Even not like this, we write even more short form as dx I bar ei hat. Okay, all these three mean the same thing. Now, dx bar transpose is f dx whole transpose, which is x transpose f transpose. Okay. Now substitute all these things in this definition. What do you get? Epsilon is ds bar square is nothing but dx bar transpose dx bar minus dx transpose dx divided by 2 times dx transpose dx, right? Is it okay?
Mm.
Good here. Let's copy this. Oh, that's amazing. You can just convert it. Wasted. Okay, anyway. This is dx bar transpose dx bar dx transpose dx divided by 2 times dx transpose dx. Okay. Now this one you simplify. We said dx bar is nothing but f dx, right?
Yes.
Dx bar transpose is dx transpose substitute here dx transpose f transpose times f dx minus dx transpose dx by 2 times now dx you can write as n vector ds times just a second. Just doing some saving. Okay. ds times n vector, right?
Yes.
Because you know that any vector you take a, it can be written as a times cosine theta x by cosine theta y j cosine theta z k, right?
Yes.
Same thing, you can take the length out, just put the direction cosines inside. Okay. Now this will give you n transpose f transpose f and minus n transpose n divided by 2 times. So n transpose n is anyway identity, so just leave this as ds square. Here you have again, here you have one ds, in this side another ds, so total is ds square. Now you can cancel out. So now you get n transpose f transpose f minus identity matrix by 2 times n. Now this one is nothing but definition of green strain tensor. Okay, previous one was Lagrange strain for a segment. Okay. So now you got this one. This is nothing but n transpose. This is strain tensor times n. Okay. So this is the quantity that is giving us stretch or contraction, or actually strain of an individual segment, or in our case an individual member. So is it clear? Hello, Kahinda. Hello, hello, Kahinda.
Yes, I'm here.
Okay, is it clear till here?
Yeah.
Okay, okay. Okay, so here we again re-explain the whatever we did in the first meeting. So right now the plan is that we will put all these direction cosines for everything, for diamond, for the comb, the entrant honeycomb, everything. So we are going to make a code which will automatically calculate for us the strain tensor. Okay. So that we don't need to solve all the simultaneous equations. All right.
Yes.
Okay. So let's do that. I didn't have food, so let me have some food. Um, After that, maybe I think too late for you. But if you're still there, it's fine. If not, let me make at least some part of the code, and tomorrow afternoon when you come, I can show you the code.
Okay.
Yeah. So you can try what you can try in the meantime is, see, we did this. First thing is, did you go back and revise all your mechanics of materials from Popo? Hello? Okay.
I'm here.
Yeah, did you go back and revise all the mechanics of materials stuff from Popo?
The one you sent me,
The
the one
textbook, yeah. Or any textbook. Did you go back and did you
I wanted to understand this first, this explanation first.
Sorry?
I wanted to understand this the first step first, this
Yeah,
calculation
but
first.
yeah, that's okay. But this is already into continuum mechanics. The mechanics of materials, it's very important to understand everything there.
Okay.
So please, if you I think it might have been a while since you took that course. So I really suggest you go back. It may take 1 day, 2 days, but read the whole Popo textbook starting to, or whichever time it takes, try to recall everything. Okay. Hello?
Yes, I'm here.
Okay. So okay. Can you study and recollect everything in mechanics of materials?
Yes.
Because if not, the Moore circle, you remember Moore circle well, how to use it?
More circle theorem. Yeah.
Okay, so
But
then what you
I
can
still need
do,
I still need to brush it up. Like maybe I will check it tomorrow.
yeah,
I'm talking about the
see
textbook.
this one. This is what I was saying. This should be actually, this is the RVE. This red one that I'm drawing,
Yes.
half of the length. That's the RVE, right? Anyway, direction cosines will not change. If you try this, then this is going to give you for this, for this, for this, for this, all of them, it will give zero strain. Okay. So this is actually coincidence. Coincidentally, affine transformation is working for this diamond, 45-degree diamond. That's why the affine gives fairly decent result. But now if you try the rest, hexagon, reentrant honeycomb, I think hexagon is like this. That's hexagon. So if you try hexagon, reentrant honeycomb and all, the stretches and that you get from here and the rotations that you get from this formula, they are not going to match uh, the one that you get from the mechanism, geometric compatibility, right? So that is where we have to make our strain tensor, concentration tensor. Is it clear?
Yes.
Okay. So I think today, let me just go to it. But meanwhile, can you try to do this thing? Just do this thing. Check for all the 4 members. Okay.
Yes.
Okay. Check the rotation too. Here I check the stretch, and you check the rotation as well. Rotation we calculated should be negative epsilon, right? So,
Yes.
so from here, if you calculate, you should get negative epsilon. Okay, you try that, okay?
Okay, I will.
Okay. Okay, thank you.
Yeah, thank you so much.
Thank you.
Dr. Nathan, are you gonna send me this record? This recording?
Yeah, I will upload to YouTube.
Okay.
Yeah.
Okay. Thank you so much.
Sure, sure.
Yeah.
Tomorrow you call me when, or you send me WhatsApp whenever you have time.
Okay.
I should be there because this NTSI summer camp, I think every day is a new schedule. I just come to know on that day. So tomorrow they put in evening, then I must be there anyhow.
When is it? When is it ending? When is it ending?
I don't remember. I'm checking. Oh my God! This is ending only 23rd.
23rd. Wow.
No. But my thing is only supposed to be only on Tuesday of next week. That's all.
Oh, Tuesday next week.
Hopefully, tomorrow should be fine, and hopefully it should be fine. Not too much more. Yeah. But anyway, you text me, I will tell you. Okay.
Okay. Okay. Thank you so much. Yeah. Thank you. Bye-bye. Yeah.
Thank you.
Yeah. Yeah.